Well, hello everybody. Welcome to Blue Marble Science. You know, when I say how stupid can you be, that's not a challenge, that's a question. But for some reason, flat earthers just can't resist. Today we're going to take a look at Rachie00000 and Anthony Riley because they've decided to give this a try. Warning, severe facial and monitor damage alert is in effect. Get out the oven mitts, push those monitors back out of punching range, and let's light this dumpster fire and have some fun. Recently, these two bastions of pseudoscience, Rachie00000 and the Sleeping Warrior, have decided to accuse me of cheating on the Cavendish experiment. And obviously I take exception to that, and we'll get into it in a few minutes. But before we go there, let's have a look at the level of scientific investigation these two get themselves involved in. First up will be Rachie, as she explores the field of advanced experimentation in the field of aerobic bottle dropping. Let's have a look.
Okay, so we have a density tower, just a little one. Oil pretty much, and water and soap. Does have a pencil and a Nerf gun end in there. I was doing other experiments and freezing it, trying to layer it in a different way. Didn't work, obviously, but worth a try, right? But yeah. So this is a density tower. I'm going to do another drop test with you and see whether this mixes. So we've got yellow on top and green, so we just need to remember yellow and green. If it mixes, obviously there shouldn't be yellow on top and green there, so we'll see what happens. So let's see.
Rachie, simply dropping your density column will not cause the liquids to mix. Regardless of their density, they're going to accelerate toward the ground at exactly the same rate. On the other hand, if relative density is what causes this, the order the liquids are in should reverse when the column is dropped. Let's see what happens. Here's the density column in a 0G airplane. It mixes up because the gas shakes it a little bit as the airplane goes into 0Gs.
Not mixing. So closer.
You didn't give your column a chance. It was only in free fall for about 0.2 of a second, and you did nothing to cause it to mix. Did you think about this, or just pour some stuff in a water bottle and give it a try?
Not mixing.
For the artistic portion of your experiment, the deep knee bends were good, the catches were clean, you kept your feet flat on the floor. I'll give you a 9.5. For the scientific portion of it, for your failure to understand what you were trying to demonstrate in the first place, and your inability to analyze your own systematic errors, I'll give you half a pity point. Let's move on. Next up, we'll have Anthony Riley and his ecological experiments with emphasis on deleterious effects of inadequate saltivity. Take it away, Anthony.
This is my egg. This is my parts per million counter. This is going to measure the parts per million of both these fluids. This is tap water, regular tap water. That is the same tap water, but it's been preloaded to save some time with some salt from this to give it a density variation. It's going to measure the density of the tap water.
No, it isn't, Anthony. You had it right the first time. It's going to measure conductivity of the solution and state that in terms of parts per million dissolved solids. You've got the wrong device. We don't measure density with a dissolved solids meter.
So while it settles down, it takes a little bit of time. Okay, that's coming in at 212 parts per million tap water. Don't know what that means. It's just a number. It could be unicorn farts. It's just a number.
Your tap water contains unicorn farts? Now I don't know whether I ought to call hazmat or animal control, Anthony.
So 212 is the recorded density of this one. Mind you, I should have showed that to the camera, shouldn't I? It's going in at 214 now. So if you want to zoom in on that, it says 214 parts per million. Okay. Back to 0. When I do it to this one is saying this is 302 parts per million. Again, if you want to zoom into that, you can have a look. Okay. So basically 200 to 300. Let's try this one again. $208. Yeah, it's about 200. Then this one's about 300. Yeah, so it's 200 and 300, right? So one's got 100 more parts per million than the other. That tells me that there is a density variation between the two. So what we're going to do is we're going to see what happens when this egg is dropped into here.
Note the steely-eyed stare as this seasoned pseudoscientist carefully determines the position of his egg.
That was nice, that, wasn't it?
It sinks and it's touching the floor. Let's take the egg out. So at the bottom at least it's getting relatively saturated. So I'm going to give it a stir to stir it up so that it evenly distributes a little bit better. Will cause the effect by adding salt. So if I can change it, because I'm the experimenter and I'm manipulating my presumed cause, my independent variable is the medium, that egg moves, I've caused it. We know the parts per million is about 300. All we need to do is pour some of this in. Hey, what do you know? The eggs immediately moved. Didn't have to wait for that, did we?
That happened too fast, Anthony. I'm not saying that adding salt won't change the specific gravity of the solution. It certainly will, given enough time, but it won't happen instantaneously. There may be a completely different explanation for what we're seeing. Those salt crystals are occupying volume, and as gravity pulls them down through that liquid, they are displacing the liquid. That results in an upward flow of the liquid. That may be the effect that we're actually seeing. Watch in slow motion as the egg begins to move before the salt crystals even reach the bottom of the egg. You made a number of mistakes here. A parts per million counter does not tell you anything about the specific gravity of the solution. You used the wrong instrument. You needed something different, like a hydrometer. Secondly, you made no attempt to remove the gravitational acceleration, which is what's causing the egg to float or sink to begin with. To do that, you're going to have to do this experiment in microgravity to prove that it's not gravity that's causing this effect. And you can't simply ignore other effects like movement of the fluid caused by pouring salt into the glass of water. Anthony, this is what we call pseudoscience. It looks like science. You try to make it look like science, but it is not science. And that's the reason we laugh at you. Okay, I think we get the idea. Let's move on to gravity, because that's what this is really all about. This is about the flat earth Newtonian theory of gravity. What is that? Well, that's the unicorn you create when you try to mix concepts of Newtonian mechanics with those of general relativity. And this is a favorite flat earth trick. They love to take parts of one theory and try to shoehorn it into the other theory. Let me tell you what I'm talking about. These are two very different theories that yield the same answer in most cases. Newton's universal law of gravitation characterizes gravity as an instantaneous force of attraction between any two masses. Now, gravity acts exactly like a force, and we see that with experiments like Cavendish, and it works very well treated as such under most circumstances. Now, Newton never gave a cause for this apparent force. He didn't know what it was. But as time went on, we understood that it breaks down under certain circumstances. For instance, using Newtonian gravity, we cannot accurately predict the precession of the orbits of the planets, nor can we predict how much light will bend when it passes by a very massive object like our sun. Einstein, on the other hand, explained the cause by introducing the concept of the bending of space-time. General relativity explains what happens in the vicinity of huge masses or when a mass moves near the speed of light. But these are conditions we don't find in our normal day-to-day lives. So put another way, Unless you park your Volvo next to a black hole or hitch a ride on the Starship Enterprise, you're probably never going to have to worry about general relativity. Here are some of the ways that flat earthers fail in these arguments. They'll make the assertion that Einstein superseded Newton. Wrong. No, he didn't. Einstein's general relativity simply refines Newton's universal law of gravitation, providing a description of gravity as the curvature of space-time which is directly related to the energy and momentum of whatever matter and radiation is present. Another thing they'll tell you is that Newton's universal law of gravitation no longer applies. Again, wrong. This is absolute fiction. Newtonian mechanics and the universal law of gravitation are taught and used exclusively throughout science and engineering with very few exceptions. Let me show you what I'm talking about. This is the curriculum from the Massachusetts Institute of Technology. This is physics subjects for the first years. Physics 1 contains that list of 11 topics that you see listed on this page. 3 of them deal with Newton's laws. Number 1 is Newtonian mechanics. Number 4 are Newton's laws. And number 8 is the universal law of gravitation. Relativity, special or general, is not taught at MIT in Physics 1, nor is it taught in Physics 2. In fact, it's taught as an elective. Engineering students are never required to even take it. And here's my favorite. Gravity is not a force. Well, that's about a half-truth. We understand gravity to be the curvature of space-time as a result of the presence of mass and energy, but that doesn't mean it doesn't act exactly like a force. It obviously does. Centrifugal force is not a force either. It acts exactly like one, and we treat it like one, however, because it only occurs and emerges in a rotating frame of reference. Gravity acts like a force, but it only emerges in the presence of a mass.
So, last night, midnight, I didn't watch it live. I watched it first thing this morning because, like, sleep's paramount these days. But anyway, Rachie00000 was arguing with Fight the Flat Earth, and obviously he gets onto gravity. Now, she asks a very basic high school level question on F equals ma. And I was gobsmacked at the obfuscation tactics that were in play. It's a very, very simple question that she asks. And what she's pointed out is that these people, these anti-flat earthers, will obfuscate at all costs when they're cornered. And she's trying to point out to them that they substitute Newton's second law in lieu of Newton's first law.
Anthony, if you or Rachie had bothered to take high school physics, you would know that Newton's first law is a special case of Newton's second law. It works like this. Newton's second law says force is the rate of change of momentum with respect to time. That means that force is actually the rate of change of the product of mass times velocity with respect to time. For a mass which is not changing, that is mass times the rate of change of velocity with respect to time, and that is acceleration. This is where F equals ma comes from. Now let's take a special case where we have a finite mass, in other words, a mass not equal to 0, but a force that's equal to 0, which requires the acceleration to be equal to 0. With no acceleration, a mass at rest will remain at rest, and a mass in motion will remain in motion at a constant velocity and moving in a straight line. This is Newton's first law. When you said we substituted Newton's second law for Newton's first law, what you literally said is we substituted an apple for an identical apple.
So she asks them, where do you get the A from in F equals ma? Now, what they're doing is they're calculating the force into existence. because they see something accelerate, they calculate the force from it, applying the sum, and then because there's an acceleration of a mass, and then they calculate the force, they claim that it doesn't matter where the force comes from, so long as they see something accelerating. But the problem is, they were talking about gravity. So because gravity is not a force, it doesn't accelerate and cannot accelerate mass.
You just flip-flop back to flat earth Newtonian physics. You're trying to combine general relativity and Newtonian mechanics, and you can't do that. Do one or the other. You don't do both at the same time. Einstein said that mass bends space-time, and mass simply follows its geodesic as it moves through space-time. That results in the acceleration we see. Newton said something that wasn't all that different. Newton's universal law of gravitation literally says mass produces an acceleration, and that acceleration is equal to the gravitational constant times the magnitude of the mass divided by the square of the distance from the center of that mass to the center of any other mass. Now, when we take that expression and we substitute it in Newton's second law, the force expression, and we give the masses different names so we can keep them separated, we get force equals mass times acceleration, which is m1 times the acceleration above, or in its more familiar form, force equals g times m1 m2 divided by d squared. Notice I'm using d in this case and not r. There's a reason for that. You guys think that r in Newton's universal law of gravitation refers to the radius of something. It doesn't. It refers to the distance between the centers of the masses.
That was nice, that, wasn't it?
Are you starting to learn anything yet, Anthony?
That's the current position in physics today, science today. But they want to apply Newtonian gravitation at all times because they want to insist that mass attracts mass, and Newton's universal gravitational theory insists that mass attracts mass. They want to apply that always, and it's not the current position in science anymore. So, Newton's first law of motion states that an object in motion or an object at rest will remain in motion or at rest unless acted upon by a force. In fact, the Flat Earth took massive issue with the fact that she didn't say an unbalanced force, because he thinks that that's important.
It is important, Anthony, because if the forces are not balanced, the net force cannot be zero. And if the net force is not zero, the acceleration cannot be zero, and Newton's first law no longer applies. Now let's listen to what Rachie was really saying. Do I have a force?
Simple yes or no answer.
Say it again. Say it again.
Do you have a force for that acceleration? Yes or no?
That acceleration is producing a force.
But Newton's first and second law says in order to have an acceleration, you need a force. So do you have a force, yes or no?
Again,
no,
right,
exactly.
Right,
so therefore, you don't have an acceleration.
Wait, stop. Right, we're going around the same things that I've schooled you on. Right, I brought Blue on specifically to talk about his.
Schooled me on.
I really have. Now, I brought Blue on to talk specifically about his Cavendish experiment. All right, so you need to explain to us how this
and
parlor
I'm
trick.
asking him about it, but you're interrupting.
No, you're not asking him about it. You're asking him about Einsteinium and the Newtonian physics, right? We're talking specifically.
I'm asking him.
Right, wait, let me finish. We are talking specifically about the mechanics behind Blue Marble Science's Cavendish experiment. Okay, so
exactly.
you are saying it's a parlor trick. So you need to explain to us how that parlor trick is achieved, specifically with maths to back up your assertions.
Which is what I'm doing. So again, can you have an acceleration without a force?
That's not telling us how the parlor trick.
Yes, it is, because it's a parlor trick if you cannot have an acceleration.
Yeah, no, that's just making an assumption. Tell us how the parlor trick is done.
Well, needless to say, Rachie was never able to come up with any explanation for this parlor trick accusation. We pressed her on it several times. She had nothing. Anthony, on the other hand, was a little more bold. In a back and forth he was having with PhD Tony in one of the comment sections, Anthony hypothesized that I was somehow or the other using an electromagnet that was off camera. But he says point blank, We know he has cheated. Really, Anthony? By your own admission, you don't have a shred of evidence to support that. I got an idea, Anthony. Pretty soon, the University of Tennessee is going to be running that experiment with their students. And you're more than welcome to come there and witness that. Somehow I don't think you're going to take me up on it, though. So I'll tell you what let's do. Let's see what we can do about answering Rachie's question. Where does the Cavendish force come from, you ask? Well, it comes from that expression, from that equation we looked at earlier, Rachie. Acceleration is the gravitational constant times the magnitude of a mass divided by the square of its distance to any other mass. Let's take Cavendish. I had a 22 kilogram mass. I had a 0.8 kilogram mass. The distance between those two was 0.15 meters. And if I plug the numbers into that expression, we get an acceleration of 6.52 times 10 to the minus 8th meters per second squared. Now, taking that acceleration into Newton's second law, we find a force of minus 52.2 times 10 to the minus 9th newtons. Notice the minus sign. This force has direction. I've decided that forces acting to the left will be negative and forces acting to the right will be positive. Well, what force acting to the right? How about this one? Now let's take the 0.8 kilogram mass and do the same thing. Plug those numbers in, you get an acceleration of 2.37 times 10 to the minus 9th meters per second squared. That results in a force of 52.2 times 10 to the minus 9th newtons. Exactly what we had before. And guess what? This now satisfies Newton's third law of motion. For every action, there's an equal and opposite reaction. And here it is. Now let's do one last thing. I'm not going to go through all of this math. This is the design sheet that I used when I analyzed what would happen with Cavendish. This has nothing to do with gravity. This sheet simply tells you how much deflection of that torsion balance will occur when a force is applied to the balance. You could apply that force any way you want. You could push on it, or you could use gravity if you like, but it predicts what the force needs to be. The average laser deflection for the tungsten wire was 32.5 millimeters. Remember that the laser multiplied the actual deflection of the beam by a factor of 10.25. So the total actual deflection was 3.17 millimeters. That would require a force of 52 times 10 to the minus 9th newtons. For all intent, that's exactly the same apparent force we calculated using Newton's universal law of gravitation, and that's not a coincidence. So I think we'll leave it there. Thanks for watching, everybody. I hope you guys enjoyed it. Don't forget to hit those like and subscribe buttons down there. Shout out, as always, to the patrons and PayPals, all the people that supported the Cavendish project. And remember, Anthony and Rachie, when I say how stupid can you be, that's not a challenge. That's just a question. Take care, everybody. See you later.